Hello there, and welcome. Before we begin our journey across the universe, take a moment to settle in and breathe slowly. If you enjoy exploring the cosmos with real, evidence-based science, don't forget to subscribe so you won't miss any discoveries. Tonight, we'll explore the universe through observation and measurement, uncovering the galaxies that fill the sky and the light that carries their stories across billions of years. Get comfortable, let your mind relax, and let's begin by asking one simple, fascinating question. How many galaxies exist in the observable universe? You begin by lifting your attention away from the ground and toward the sky above you. The night appears quiet, but science shows that it is filled with structure, motion, and measurable patterns. Light arriving at your eyes has traveled across space for years, centuries, and sometimes billions of years. Each faint point is evidence, carrying information about distance, energy, and origin. You are not guessing at what exists beyond Earth. You are receiving signals that can be tested, compared, and understood. A galaxy is not a vague collection of stars. It is a gravitationally bound system containing billions or even trillions of stars, along with gas, dust, planets, and large amounts of unseen mass known as dark matter. These systems obey physical laws that can be measured with instruments and equations. When astronomers ask how many galaxies exist, they are not asking philosophically. They are asking how many such systems can be detected, classified, and counted within the limits of observation. You may wonder why this number matters. Counting galaxies helps scientists understand how matter is distributed across space. It provides clues about how the universe evolved from a nearly uniform state after the Big Bang into the structured web seen today. The number of galaxies influences models of cosmic expansion, gravity, and the behavior of matter over time. Each count refines the picture of how space itself has changed. The act of counting in astronomy is careful and slow. You cannot simply look at the sky and tally what you see. Many galaxies are too faint to be detected without long exposures. Others are hidden behind dust or lie at distances where their light is stretched into wavelengths invisible to the human eye. Astronomers rely on telescopes that collect light for hours or days, sensors that measure precise wavelengths, and statistical methods that account for what cannot be seen directly. As you rest with this idea, it becomes clear that observation is the foundation of all astronomical knowledge. The universe does not reveal itself all at once. Information arrives photon by photon, each particle of light carrying a small piece of a much larger story. By measuring brightness, color, and motion, scientists infer distance, mass, and composition. Nothing is assumed without evidence that can be checked by others. You are living inside one galaxy, the Milky Way, which contains hundreds of billions of stars. For much of human history, this galaxy was thought to be the entire universe. Only in the early 20th century did observations show that faint spiral shapes in the sky were separate galaxies far beyond our own. That realization instantly expanded the known scale of existence. Counting galaxies became a way of mapping reality itself. The question of how many galaxies exist is shaped by limits that physics imposes. Light travels at a finite speed. The universe has a measurable age. This means there is a boundary beyond which light has not yet reached Earth. Scientists call this region the observable universe. Galaxy counts apply only within this visible volume, not because anything beyond is unreal, but because information from those regions has not had time to arrive. You find comfort in the idea that limits are clearly defined. Astronomers do not claim to know what cannot be observed. They work carefully within what can be measured. When surveys are conducted, they scan specific areas of the sky, detect objects above known brightness thresholds, and correct for known biases. This methodical approach allows estimates to improve over time without sudden leaps or unsupported claims. Each galaxy counted represents a balance between gravity and motion. Stars orbit within these systems according to predictable rules. Gas clouds collapse and form new stars. Supernovae spread heavier elements into surrounding space. These processes repeat across billions of systems, governed by the same physical laws everywhere they are measured. Counting galaxies is also counting repetitions of known physics across vast distances. As your breathing slows, You can imagine astronomers patiently working with images filled with tiny points of light. Each point is analyzed, its spectrum measured, its distance estimated. Objects that appear similar are grouped and compared. Errors are acknowledged and refined. Over decades, this steady accumulation of data leads to more accurate totals. The process is quiet, disciplined, and continuous. You may notice that this careful counting challenges intuition. The human mind is shaped by everyday numbers, not by billions upon billions. Science provides tools that extend understanding beyond instinct. Large numbers are handled through averages, distributions, and models that can be tested against observation. In this way, even the largest scales become approachable. The question of galaxy numbers also connects to how structure forms. Galaxies are not evenly scattered. They cluster into groups, chains, and vast filaments separated by enormous voids. This arrangement reflects the influence of gravity acting over billions of years on small initial differences in matter density. Counting galaxies within these structures reveals how matter flows and gathers. As you rest with these ideas, you sense that counting galaxies is not about awe alone. It is about clarity. Each improved estimate narrows uncertainty. Each deeper observation refines understanding. The universe becomes not smaller, but more precise. Knowledge replaces vagueness with measured detail. You remain gently aware that this question began with looking up. The same sky that once appeared empty now reveals layers of structure when studied carefully. Even without seeing individual galaxies, you know they are there because their light has been measured, catalogued, and compared. This understanding settles quietly in your mind. As the night continues, you hold a simple truth. The universe can be counted because it follows consistent rules. Those rules allow light to travel, matter to gather, and observers to measure what arrives. With each observation, the darkness becomes more defined, and the vastness above gains shape through evidence. You gently consider how this measured approach depends on understanding what a galaxy truly is, how it differs from smaller star groupings, and how gravity defines its boundaries. Precision in definition shapes precision in counting. As attention settles, the mind becomes ready to explore what astronomers mean when they identify these vast systems, and how careful classification supports every number that science provides. These distinctions rest on motion, mass, and long-term stability observed consistently across cosmic distances through repeated measurement. You rest with the understanding that clarity begins with definition. Before anything can be counted, it must be identified accurately. In astronomy, a galaxy is not simply a bright shape or a pattern of stars. It is a physically bound system held together by gravity, containing stars, gas, dust, stellar remnants, and a dominant component that cannot be seen directly, but reveals itself through its effects. This unseen mass is called dark matter, and it plays a central role in defining what a galaxy is. You learn that gravity is the key requirement. A galaxy must be massive enough that its components remain bound over billions of years. Stars within a galaxy orbit a shared center of mass. Gas clouds move according to the same gravitational structure. These motions are measured through shifts in light known as redshift and blueshift, allowing astronomers to calculate speeds and infer mass. If the mass were insufficient, the system would disperse, and it would not qualify as a galaxy. You notice that size alone does not determine classification. Some galaxies are vast, stretching hundreds of thousands of light-years across. Others, called dwarf galaxies, may contain only a few million stars. What unites them is not scale but stability. Each has enough total mass, including dark matter, to maintain a coherent structure over cosmic time. This distinction matters deeply when scientists count how many galaxies exist. You may wonder how this differs from a star cluster. Star clusters are groups of stars formed together, often within a galaxy. They can be dense and visually impressive, but they lack sufficient mass to retain dark matter halos. Their stars orbit one another loosely and are more vulnerable to disruption by external gravitational forces. Over time, many star clusters dissolve. Galaxies endure. The presence of dark matter is confirmed through observation, not assumption. When astronomers measure how fast stars orbit at different distances from a galactic center, They find that visible matter alone cannot explain the motion. Stars far from the center move faster than expected. This consistent pattern, observed across many systems, indicates additional mass distributed in an extended halo. This evidence supports the definition of a galaxy as a system dominated by gravitational structure beyond what can be seen. You remain calm as complexity settles into clarity. Galaxies come in different shapes, classified based on appearance and internal motion. Spiral galaxies have rotating disks with winding arms and central bulges. Elliptical galaxies are more rounded, with stars moving in varied directions. Irregular galaxies lack a defined shape, often shaped by interactions or internal turbulence. These classifications are descriptive tools, not separate categories of physics. Despite differences in form, all galaxies obey the same fundamental laws. Gravity governs motion. Nuclear fusion powers stars. Gas cools, collapses, and forms new stellar generations. These processes are observed repeatedly across many systems, confirming that galaxies are not unique events but recurring outcomes of known physical conditions. You may find reassurance in how astronomers verify classification. Measurements are repeated using different instruments. Data is shared openly. Independent teams analyze the same objects and reach consistent conclusions. This collective process refines definitions and reduces uncertainty. A galaxy is identified not by impression, but by evidence. As you continue to reflect, you understand why defining a galaxy carefully matters for counting them. If star clusters were mistakenly included, numbers would inflate inaccurately. If faint dwarf galaxies were overlooked, totals would be underestimated. Precision in definition ensures that counts reflect reality rather than assumption. You also learn that galaxies interact. They pass near one another, exchange material, and sometimes merge. These interactions can change shape but do not erase identity. Even during mergers, the gravitational structures remain traceable. Over time, two galaxies may become one larger system, but this process follows predictable dynamics that can be modeled and observed. You breathe slowly, aware that every galaxy identified represents a long-term balance between motion and gravity. This balance can be tested mathematically and observed directly. It does not depend on perspective or belief. It depends on mass, velocity, and time. As your mind rests, you see that understanding what a galaxy truly is creates a stable foundation. With clear criteria in place, astronomers can look outward with confidence, knowing what to include and what to exclude. This careful groundwork allows numbers to carry meaning rather than confusion. The quiet realization settles that galaxies are not merely distant lights, but structured systems governed by universal laws. Recognizing them requires attention to motion, mass, and persistence. With this understanding, the universe becomes organized rather than overwhelming, and the vast population of galaxies becomes something that can be approached through careful observation, measurement, and patient study grounded in evidence that continues to arrive with every collected photon. You begin from a place that is familiar, even if it cannot be seen directly. Earth moves quietly within a vast system of stars known as the Milky Way. This galaxy contains hundreds of billions of stars arranged in a rotating disk with a central concentration of older stars. Measurements of stellar motion show that the entire system is bound together by gravity and surrounded by a large halo of unseen mass. This is the environment where all human observation begins. From within the Milky Way, your position is not central. You orbit the galactic center at a distance of about 26,000 light-years, moving at a measurable speed determined by gravity. Astronomers calculate this motion by tracking the positions and velocities of nearby stars. These measurements confirm that the Milky Way is a typical large spiral galaxy, neither unusually massive nor unusually small. As your awareness gently widens, you learn that the Milky Way does not exist in isolation. It is part of a small collection of galaxies known as the Local Group. This group contains more than 50 known galaxies, ranging from large spirals to faint dwarf systems. They are bound together by gravity and move through space in relation to one another. Their motions can be measured with precision using shifts in light frequency. The two largest members of this group are the Milky Way and the Andromeda Galaxy. Andromeda lies about 2.5 million light-years away and is approaching slowly due to mutual gravitational attraction. This motion is not guessed. It is measured directly through the slight blue shift in Andromeda's light. Such measurements confirm that galaxies behave as physical objects with mass and velocity. Around these large systems orbit many smaller galaxies. These dwarf galaxies contain fewer stars and lower total mass, but they remain gravitationally bound. Their existence is confirmed through careful observation of stellar populations and motion. Many are faint and difficult to detect, requiring sensitive instruments and long observation times. You notice that distance now becomes essential. To understand which galaxies belong to the same group, astronomers must know how far away they are. Nearby galaxies can be resolved into individual stars, allowing distance estimates through well-established methods. This clarity allows scientists to separate local systems from more distant background galaxies that only appear close together from Earth's viewpoint. As you settle deeper into the idea of scale, you learn that the local group is part of a larger structure called the local sheet, which itself is part of an even larger region influenced by gravity. Galaxies arrange themselves into groups and clusters, forming a web-like structure across space. This arrangement is not random. It reflects the distribution of matter shaped over billions of years. The Milky Way's neighborhood is mapped using careful surveys of the sky. Each detected galaxy is catalogued, its position recorded, and its motion measured. When patterns emerge, astronomers test whether gravity can explain them. When it does, the structure is confirmed. This methodical approach ensures that cosmic maps are reliable. You rest with the understanding that knowing your cosmic address depends on measurement rather than appearance. Galaxies that look similar may lie at vastly different distances. Only by analyzing light and motion can their true positions be known. This is why early astronomy underestimated the size of the universe. The tools were not yet precise enough. As instruments improved, nearby galaxies were revealed one by one. Each discovery refined the boundary between what belongs to the local environment and what lies far beyond. This gradual expansion of known space did not happen suddenly. It unfolded through decades of patient observation. You may feel a sense of calm in realizing that astronomers build outward from what is closest. Understanding the Milky Way provides a reference point. Nearby galaxies offer comparison. Together, they create a foundation for interpreting more distant systems. Without this local knowledge, larger scales would be harder to understand. The local group also provides insight into galaxy behavior. Interactions between galaxies can trigger star formation or alter shape. Evidence of past encounters is visible in streams of stars and distorted structures. These features are studied to understand how gravity shapes galaxies over time. You continue to rest as the idea settles that the universe reveals itself in layers. Each layer depends on careful measurement of distance, motion, and light. Starting from Earth, moving through the Milky Way, and extending to nearby galaxies, scientists construct a reliable framework. This framework supports all larger estimates of galaxy numbers. As your breathing remains slow, you sense that stepping beyond the local neighborhood requires even greater precision. Measuring distances across millions and billions of light-years demands methods that build on what is learned nearby. The ability to place galaxies accurately in space becomes the key that allows the cosmic map to extend far beyond familiar surroundings, relying always on light as the messenger that quietly carries distance information across the vastness of space. You settle into the idea that distance in space cannot be measured by travel or direct reach. Instead, it is measured by light and geometry, using methods that rely on observation rather than motion. Astronomers determine how far away an object is by examining how its light behaves over time and space. Each method is grounded in physics that can be tested nearby before being applied farther away. You begin with the most direct technique known as parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. This shift is small, but it is measurable with precise instruments. By observing the angle of this shift and knowing Earth's orbit size, astronomers calculate distance using simple geometry. This method works reliably for stars within a few thousand light-years. You notice how this approach depends on stability and repetition. Measurements are taken months apart and compared carefully. Errors are accounted for. The closer the star, the larger the apparent shift. This predictable relationship confirms that the method is sound. Parallax provides the first rung of what astronomers call the distance ladder, a sequence of techniques that extend outward. Beyond the reach of parallax, astronomers rely on objects with known brightness. Certain stars vary in brightness over time in a regular and predictable way. These stars, called Cepheid variables, pulse at rates directly related to their true luminosity. By measuring how bright they appear from Earth and comparing that to how bright they truly are, distance can be calculated. You remain calm as you see how this method builds on earlier knowledge. Cepheid variables are first studied nearby, where distances are known through parallax. This calibration ensures accuracy before the method is applied to farther regions. Once verified, Cepheids become reliable markers for measuring distances to nearby galaxies. As your awareness expands, you learn that even Cepheid variables have limits. At greater distances, their light becomes too faint to detect clearly. Astronomers then turn to more energetic events, such as type Ia supernovae. These stellar explosions occur when a specific kind of star reaches a known mass limit. Because this process is consistent, the resulting explosion has a predictable brightness. You breathe steadily as you understand how these supernovae act as distance markers across vast reaches of space. They are bright enough to be seen across billions of light years. Their light curves, which show how brightness changes over time, confirm their identity. This consistency allows astronomers to measure distances far beyond individual galaxies. You notice that no single method stands alone. Each technique overlaps with others, creating checks and balances. Parallax confirms Cepheids. Cepheids confirm supernova measurements. This layered approach reduces uncertainty and increases confidence. Distance measurement becomes a system, not a guess. You also learn that light itself carries distance information through redshift. As the universe expands, light traveling across space is stretched to longer wavelengths. By measuring this stretching, astronomers determine how fast an object is moving away. When combined with calibrated distances, redshift becomes another powerful tool for mapping space. As your mind rests, you see how careful astronomers are to separate motion caused by expansion from motion caused by local gravity. Nearby galaxies may move toward or away from one another due to gravitational interaction. These motions are measured independently to avoid confusion. Precision remains the guiding principle. Distance measurement is never rushed. Observations are repeated, instruments are refined, and results are compared across teams. When discrepancies appear, methods are reevaluated. This patience ensures that distance estimates improve steadily rather than dramatically. You find comfort in how these techniques rely on physics tested on Earth. Geometry does not change across space. The behavior of light remains consistent. Nuclear processes inside stars follow known rules. Because these principles are universal, they can be trusted far from home. As the scale grows larger, small uncertainties become significant. Astronomers account for this by using statistics and large samples. Patterns emerge when many objects are measured. Individual errors average out, revealing reliable trends. This approach allows distance estimates to remain meaningful even at immense scales. You rest with the understanding that measuring distance is essential for counting galaxies. Without knowing how far away objects are, astronomers cannot determine whether faint points of light are small nearby systems or massive distant ones. Distance gives context. It transforms brightness into size and motion into structure. As your breathing slows, you sense that this careful ladder of measurement quietly supports every map of the universe. Each rung depends on the one below it. Each step outward is earned through verification. With distance firmly established through light and geometry, the universe becomes something that can be charted reliably, allowing observers to look deeper into space with confidence that what they see can be placed accurately within the vast three-dimensional structure revealed by patiently measured starlight. You begin by imagining the instruments that extend human vision beyond natural limits. Early astronomers relied on lenses and mirrors that captured more light than the human eye alone could perceive. These telescopes revealed that stars and nebulae were not points of light alone, but structured systems. With patience, the sky became measurable rather than mysterious. Ground-based telescopes provided the first significant advances in galaxy detection. Large mirrors collect faint light and focus it onto detectors. Observers carefully track positions over nights and years, measuring motion, brightness, and shape. These measurements allow astronomers to distinguish nearby stars from distant galaxies. The method is simple in principle but requires precision and repetition. Photographic plates became a key tool in the early 20th century. They recorded light for long periods, capturing faint objects invisible in real time. Astronomers could then examine plates systematically, cataloging galaxies one by one. Each faint spiral or elliptical was confirmed through repeated observation. The process emphasized patience and care over speed. You notice that even small improvements in telescope quality dramatically increase the number of galaxies detected. Larger apertures capture more light, revealing faint systems. Higher resolution separates closely spaced objects that previously appeared as a single blur. Advances in mount stability and tracking allow long exposures without blurring, ensuring the accuracy of each measurement. As your awareness settles, you consider the role of space-based telescopes. Freed from Earth's atmosphere, these instruments avoid distortion caused by turbulence and absorbance. The Hubble Space Telescope, launched in 1990, represents a major leap. Its images reveal thousands of galaxies in tiny fields of view. What once required extensive observation from Earth can now be captured with clarity and depth from orbit. You understand that technological improvement is cumulative. Each generation of instruments builds upon prior knowledge. Filters and sensors isolate specific wavelengths of light, allowing astronomers to detect objects at various distances and stages of development. Infrared detectors reveal systems hidden behind interstellar dust, while ultraviolet and visible light trace young and old stellar populations. Observational surveys provide systematic coverage. Telescopes scan designated regions of the sky repeatedly, measuring brightness and position. Automated software identifies candidates for galaxies, which are then verified through further observation. Statistical analysis corrects for detection limits and biases, ensuring that the final counts reflect reality rather than the limitations of technology. You learn that some discoveries challenge prior assumptions. Faint galaxies often outnumber those visible in earlier surveys, increasing total estimates. Small dwarf systems are revealed in nearby groups, while distant faint spirals expand the census of the universe. Each technological advance reshapes understanding, but always grounded in observation. The development of wide-field imaging also changes perspective. Telescopes that capture larger portions of the sky reduce uncertainty caused by sampling only small regions. Patterns in galaxy distribution become evident, confirming that galaxies are not scattered randomly but follow large-scale structures shaped by gravity. Technology allows these patterns to emerge clearly. You notice that data from multiple telescopes is often combined to increase depth and reliability. Observations in different wavelengths complement one another, confirming distances, motion, and composition. Collaboration ensures that no single measurement is treated as absolute. Repetition and cross-verification produce the consistent counts that are necessary for understanding the true number of galaxies. As your attention settles, you realize that every galaxy in the count depends on the instruments used to detect it. The faintest systems are invisible without the most sensitive detectors. The most distant systems are only revealed through long exposures and precise measurement. Telescopes transform observation from estimation to quantifiable knowledge. You rest with the thought that the advancement of technology is inseparable from the expansion of understanding. The universe remains vast, but each improvement in instruments allows it to be mapped more accurately. The sky becomes a measurable landscape, each faint point of light verified and counted, extending the quiet, disciplined work of observation farther and farther into space. Even as the night sky appears unchanging to the eye, technology reveals layers of galaxies previously unseen, demonstrating that careful measurement can continuously deepen human understanding. These instruments create the foundation for exploring the faintest, most distant galaxies, laying the path for observing details that were once beyond imagination and providing the data necessary for estimating the total number of galaxies with confidence. You begin with the idea that sometimes the universe is revealed in the smallest patch of sky. In 1995, astronomers used the Hubble Space Telescope to focus on a seemingly empty region in the northern constellation of Ursa Major. The field was tiny, less than 1/10 the diameter of the Moon as seen from Earth, yet it would become one of the most significant observations in astronomy. For 10 consecutive days, Hubble collected light from this small area. The telescope's instruments captured photons that had traveled billions of years. Exposure times were long enough to record extremely faint objects, far beyond what ground-based instruments could detect. Each photon arriving at the detector contributed to a growing image that revealed the distant universe in unprecedented detail. When the images were processed, the results were astonishing. Thousands of galaxies appeared in a space that seemed empty to the naked eye. Spirals, ellipticals, and irregular systems crowded the frame, each representing billions of stars. Some galaxies appeared as they were billions of years ago, their light stretched by the expansion of space to longer, redder wavelengths. This observation dramatically increased estimates of galaxy abundance. You notice that the Hubble Deep Field illustrates how much light carries information. Even the faintest smudges are not random. They reveal structure, shape, and composition. Scientists analyze the light from each galaxy to determine distance, star formation rate, and chemical makeup. This careful work confirmed that galaxies exist in far greater numbers than previously imagined. The methodology behind the deep field demonstrates patience and precision. Observers selected a patch of sky away from bright stars and galaxies, minimizing interference. The telescope was pointed steadily for hours at a time, capturing each photon as it arrived. Multiple exposures were combined to increase signal and reduce noise. This meticulous approach shows that meaningful measurement requires time and care. You learn that the Hubble Deep Field also provides insight into cosmic evolution. Many galaxies appear irregular or distorted, indicating that early in the universe, galaxies were smaller, more chaotic, and actively forming stars. Others display mature spiral or elliptical structures, suggesting that evolution toward present-day forms occurred over billions of years. Observation allows the universe's history to be traced in a single image. The discovery also highlights the limits of perception. Even with Hubble, some galaxies are so faint that only statistical methods suggest their presence. Astronomers use these methods to extrapolate total numbers, estimating the population of galaxies beyond the directly observed field. Careful reasoning ensures that these estimates remain grounded in evidence, not speculation. You settle into the idea that the deep field is not just a photograph. It is a dataset. Each pixel contains measurable light, each galaxy has quantifiable properties, and each observation can be reproduced with future instruments. Verification is central. The results are not a guess but a precise record of what the telescope measured over many hours. This observation reshapes perspective. What seemed like empty space is now recognized as densely populated with galaxies. The universe is vast, but structured and measurable. Even within a tiny fraction of the sky, the abundance of galaxies demonstrates the scale and complexity of cosmic architecture. As your mind rests, you notice that the deep field reveals galaxies at different stages of development. Some are actively forming stars, while others are older and less active. This diversity within a small patch reflects the range of conditions across the observable universe. Observation provides both quantity and qualitative understanding. You understand that the Hubble Deep Field is a reminder of the importance of patience in science. Long exposures, precise instrumentation, and careful planning produce results that change understanding fundamentally. Each faint galaxy detected represents countless photons measured with precision, contributing to a growing picture of the universe's vastness. Breathing slowly, you rest with the knowledge that even a tiny fraction of the sky can reveal billions of galaxies when observed carefully. The image demonstrates how modern telescopes allow the universe to be measured systematically, transforming what was once thought empty into a densely populated cosmic landscape. These observations lay the groundwork for understanding how galaxies are distributed across the observable universe, providing the foundation for mapping larger structures and estimating total counts with confidence. You begin by considering why observation has limits, even with the most powerful telescopes. Light travels at a finite speed, and the universe has existed for a finite time. This means there is a maximum distance from which light could have reached you since the beginning of cosmic expansion. The region defined by this limit is called the observable universe. Each galaxy you see exists at a specific distance, measured in billions of light years. When light leaves a galaxy, it begins a journey across space. The farther away the galaxy, the longer its light has traveled. Observing distant galaxies allows you to see them as they were in the past, revealing a record of cosmic history. You notice that this perspective is constrained. Beyond a certain distance, light has not yet had time to reach Earth. Those regions are physically present, but invisible to observation. The observable universe is a volume determined by the speed of light and the universe's age, approximately 13.8 billion years. Accounting for expansion, this volume extends roughly 46 billion light-years in all directions. Cosmic expansion also affects what you see. Space itself stretches, increasing the distance between galaxies over time. Light traveling through expanding space is stretched to longer wavelengths, a phenomenon called redshift. Measuring redshift provides both velocity information and relative distance, allowing astronomers to map the observable universe with precision. You settle into the concept that distance is not static. A galaxy observed at 10 billion light-years is now much farther away due to ongoing expansion. Despite this, the light that reaches your instruments reflects conditions at the time it was emitted. Astronomers must carefully correct for expansion to determine the galaxy's current position and history. Defining the observable universe also provides context for counting galaxies. Only systems within this volume can be detected directly. Beyond it, galaxies exist but remain unobservable. This does not diminish their reality. It simply defines the boundaries of what can be measured reliably using light. You notice that understanding these limits requires precise measurement of cosmological parameters. The Hubble constant, which quantifies the universe's expansion rate, influences the size of the observable universe. Measurements of background radiation, galaxy distribution, and supernovae provide consistent data to refine this value. This allows the observable volume to be defined accurately. Even within the observable universe, not all galaxies are detectable. Some are extremely faint, small, or obscured by dust. Surveys use statistical methods to account for these missing systems, extrapolating counts based on observable samples. The combination of direct observation and statistical modeling produces estimates of total galaxy numbers with quantifiable uncertainty. You remain calm as you consider the implications of these limits. The observable universe is vast, yet it is measurable. It forms a framework for all astronomical study, setting the stage for mapping structures, analyzing galaxy formation, and testing cosmological models. Knowledge arises not from imagination but from careful observation within these defined boundaries. You learn that understanding the observable universe also clarifies why galaxies appear differently at different distances. Nearby galaxies are seen in detail with resolved stars and structures. Farther galaxies appear as faint shapes, often irregular due to early formation stages. The combination of distance, light travel time, and resolution shapes all observations. As your attention settles, you sense the balance between vastness and limitation. While the universe beyond observation is unknown, the region accessible to light provides a coherent, measurable structure. This perspective allows astronomers to count galaxies with confidence, knowing precisely the volume under consideration and the physical principles governing the measurement of distance, brightness, and motion. Breathing slowly, you rest with the awareness that the observable universe is both immense and well-defined. Bound by light and time, it offers a reliable framework for exploring the distribution of galaxies. Within this volume, Careful measurement and systematic observation transform the seemingly infinite sky into a mapped landscape, providing the foundation for understanding the large-scale structure of cosmic matter, the dynamics of galaxy formation, and the total number of systems that inhabit the universe. You begin with the observation that visible matter alone cannot explain the motions of stars in galaxies. When astronomers measure how fast stars orbit around the centers of spiral galaxies, they find that outer stars move far faster than expected based solely on the gravitational pull of visible stars and gas. This discrepancy points to the presence of additional mass that cannot be seen. This unseen component is called dark matter. Its existence is inferred from gravitational effects, not direct observation. Though it emits no light, it exerts a measurable influence on the motion of stars, the rotation of galaxies, and the paths of light from more distant objects. The evidence is consistent and reproducible, providing a clear indication of its role in galactic structure. You notice that rotation curves, which plot orbital speed against distance from the galactic center, remain flat at large radii rather than declining. According to Newtonian physics, stars farther from the center should move more slowly if only visible matter were present. Observations, however, show constant velocities, requiring an extended halo of unseen mass. This pattern is evident across many galaxies. Gravitational lensing offers further evidence. Massive objects, including dark matter halos, bend light from background sources. By measuring distortions in the shapes of distant galaxies, astronomers map the distribution of mass, including components that cannot be detected by emitted light. These measurements confirm that most of a galaxy's mass is not luminous but hidden in an extended structure. You breathe slowly as you consider how dark matter influences formation. Galaxies arise where concentrations of dark matter create potential wells, drawing gas and stars into gravitationally bound systems. Without these halos, galaxies as observed could not form or remain stable. Dark matter guides the assembly of structure on scales ranging from dwarf galaxies to galaxy clusters. Even the shape of galaxies is affected. Spiral disks form within dark matter halos, which provide gravitational stability, allowing stars to orbit in ordered patterns. Elliptical galaxies result from mergers and interactions within combined halos. Irregular galaxies often reflect ongoing dynamical processes within less uniform halos. Observed diversity aligns with models that include dark matter as a dominant component. You notice that dark matter also influences the large-scale distribution of galaxies. Filaments, walls, and voids in the cosmic web correspond to regions of higher and lower dark matter density. Galaxies cluster along these structures, and their motion reflects the gravitational pull of underlying mass. Observing these patterns provides insight into the unseen scaffolding of the universe. Evidence for dark matter extends beyond galaxies. Galaxy clusters contain more mass than accounted for by visible stars and gas. Hot gas within clusters emits X-rays, yet the total gravitational pull measured from motion and lensing requires additional mass. The consistency of this finding across multiple systems strengthens confidence in the presence of dark matter. You understand that dark matter is not directly observed, but its effects are precise and predictable. Models that include dark matter reproduce observed velocities, distribution, and large-scale structure. Without it, many features of the universe would remain unexplained. Observation, rather than speculation, provides the foundation for this conclusion. As your mind rests, you consider that galaxies are shaped by both visible and invisible components. Stars and gas follow paths dictated by gravitational influence, while dark matter provides stability and long-term structure. Measuring galaxies without accounting for dark matter would produce incomplete or inaccurate results. You remain calm in the realization that most of a galaxy's mass is hidden, yet measurable through its gravitational influence. This invisible component sets the stage for understanding how galaxies form, interact, and evolve. With dark matter as a constant presence, astronomers can interpret motions, distribution, and formation histories reliably, providing a deeper insight into the hidden architecture of the universe. Breathing slowly, you sense that the presence of dark matter explains why galaxies exist in the configurations observed. Their rotation, clustering, and evolution are all shaped by this unseen mass, quietly guiding structure across cosmic scales. The careful study of light, motion, and gravity reveals not only the visible universe but also the hidden framework that supports it, preparing your mind to understand how galaxies grow and change over billions of years. You begin by considering the universe shortly after the Big Bang, a time when matter was nearly uniform. Slight variations in density existed, detectable today in the cosmic microwave background. These tiny differences in mass provided the seeds for future structure. Regions slightly denser than their surroundings began to attract more matter through gravity, initiating the slow assembly of the first galaxies. Gas accumulates in these overdense regions, cooling gradually as it radiates energy. Hydrogen and helium, the primary components of the early universe, condense under gravitational pull. Small clumps merge, forming larger structures in a process that continues over millions and billions of years. These clumps, initially irregular and chaotic, eventually become the precursors of the first galactic systems. You notice that star formation begins within these early clouds. When gas density reaches critical thresholds, nuclear fusion ignites in stellar cores. These first stars are massive and short-lived, producing heavy elements through fusion and dispersing them via supernovae. These elements enrich the surrounding medium, providing the raw material for subsequent generations of stars and planetary systems. As you settle into this slow progression, you observe that galaxies grow in complexity over time. Small systems merge with neighbors, combining mass, angular momentum, and gas. Mergers produce structural changes, irregular shapes, starbursts, and eventually more stable configurations such as spiral disks or elliptical forms. Observations show that distant galaxies often appear irregular, confirming that early galaxies were dynamically active. High redshift surveys allow you to look back billions of years. Light from these galaxies takes enormous time to reach Earth, revealing systems as they existed long ago. Younger galaxies tend to be smaller, clumpier, and more active in star formation than nearby mature galaxies. By comparing distant galaxies with local ones, astronomers reconstruct evolutionary pathways and understand how structure develops over cosmic time. You notice that star formation is regulated by the availability of gas. Dense regions produce stars rapidly, while gas depletion or feedback from supernovae and active galactic nuclei slows the process. Observations confirm that the rate of star formation varies across galaxies and epochs. In the early universe, star formation rates were significantly higher, consistent with the presence of abundant primordial gas. Dark matter halos remain central throughout this evolution. Gas collapses within gravitational wells defined by dark matter, guiding the assembly of visible components. Without these halos, gas would disperse, and galaxies could not form stable structures. Simulations of structure formation consistently reproduce galaxy properties only when dark matter is included, matching observations across cosmic time. You rest with the knowledge that mergers shape galaxy populations. Some galaxies grow by absorbing smaller systems, increasing mass and altering morphology. Interactions trigger bursts of star formation and can redistribute angular momentum. Observationally, tidal tails and distorted structures in interacting galaxies provide clear evidence of these processes at work, both nearby and at high redshift. You observe that feedback mechanisms play a role in regulating galaxy growth. Energy and momentum from supernovae, stellar winds, and black hole activity can expel gas from galaxies, slowing star formation and shaping evolution. These processes maintain a balance, preventing runaway growth and influencing the distribution of mass within galaxies. Evidence from emission lines, outflows, and kinematic measurements confirms the impact of feedback on galactic evolution. Galaxies also evolve chemically. Early systems are metal-poor, containing mostly hydrogen and helium. Successive generations of stars enrich galaxies with heavier elements, measurable in stellar atmospheres and gas clouds. Astronomers observe these metallicity patterns to infer the history of star formation and gas accretion. Distant young galaxies are less enriched, consistent with fewer stellar generations, while nearby galaxies show higher metallicities. You notice that morphology and dynamics evolve together. Disks form as gas cools and angular momentum is conserved. Elliptical galaxies result from mergers that randomize stellar orbits. Irregular systems reflect ongoing accretion or interaction. Observations confirm that galaxy types are linked to their formation history, not merely appearance, providing a reliable record of cosmic processes over time. You settle into the understanding that galaxy formation is a slow, continuous process. Stars ignite, galaxies merge, and structures stabilize over billions of years. Light from distant galaxies serves as a historical record, allowing measurement of age, composition, and evolution. Each observation is a data point in reconstructing a timeline of cosmic growth. You recognize that simulations play a complementary role. Numerical models that incorporate gravity, gas dynamics, star formation, and dark matter produce structures that closely match observed galaxies. Comparison between theory and observation confirms that the physical principles driving galaxy formation are well understood, even across immense distances and timescales. As you breathe slowly, you realize that observing galaxies at different distances provides a natural time machine. Light itself measures time, revealing the gradual transformation from simple clumps to mature systems. The story of galaxy formation is written in photons, and careful observation allows the unfolding of billions of years to be traced, layer by layer, revealing the universe's ongoing development in measured, evidence-based steps. Time settles in your mind as a gentle continuum. Galaxies are not instantaneous phenomena. They are processes measured over cosmic epochs. Each star, each merger, each feedback event contributes to an evolving population. Observation confirms this sequence, providing a reliable record of growth and change. You rest with the understanding that the universe's complexity unfolds slowly, patiently, and predictably, as measured through light that carries both structure and history across billions of years. Light from early galaxies continues to arrive, carrying information that allows astronomers to reconstruct formation histories, chemical evolution, and interactions. Every observed system contributes to a consistent picture. Galaxies form gradually, grow through mergers and star formation, and evolve toward structures observed nearby. This measured progression provides both clarity and a calm sense of order in the vast cosmos. You gently reflect that the universe's past is accessible through careful measurement. By studying formation, growth, and evolution, astronomers understand not only what galaxies are, but how they became what they are today. The interplay of gas, stars, dark matter, and time is observable and predictable, revealing a universe that evolves slowly, steadily, and measurably. You begin by considering how knowledge evolves with observation. Early counts of galaxies were limited by the instruments available at the time. Telescopes with smaller apertures could detect only the brighter, more prominent systems. Fainter galaxies, dwarf systems, and distant high-redshift galaxies were missed entirely. Early estimates reflected this limitation, producing a lower bound rather than a definitive number. You notice that each technological improvement reveals additional galaxies. Larger telescopes collect more light, enabling the detection of faint and distant systems. Improvements in detectors, such as charge-coupled devices, CCDs, increased sensitivity while reducing noise. Longer exposures captured photons that were previously invisible, making previously undetectable galaxies measurable. Surveys have become deeper and more systematic over time. The Hubble Deep Field, the Hubble Ultra Deep Field, and subsequent space-based surveys revealed thousands of faint galaxies in tiny patches of sky. Ground-based wide-field surveys complemented these by mapping larger regions. Each survey added layers of information, expanding the catalog of known galaxies and highlighting how previous estimates were incomplete. You learn that the methods used to count galaxies also evolved. Early studies often relied on direct observation, where astronomers visually identified systems on photographic plates. Later, automated detection and statistical modeling allowed scientists to account for galaxies too faint to be detected directly. These models extrapolate from observed samples, estimating populations in regions beyond the reach of current instruments. Uncertainty remains a natural part of this process. Even with modern instruments, Some galaxies are so faint or distant that they lie below detection thresholds. Astronomers quantify these limits and incorporate them into calculations, producing counts with explicit margins of error. Transparency about uncertainty allows estimates to be interpreted responsibly. You notice that the galaxy count also depends on definition. Dwarf galaxies, satellite systems, and faint irregulars may or may not be included depending on criteria. Including or excluding these systems changes totals significantly. Modern studies aim for consistent classification, using gravitational binding, size, and structure as measurable criteria rather than subjective appearance. Observational techniques continue to improve. Multi-wavelength imaging reveals galaxies obscured in visible light. Infrared observations penetrate dust, revealing hidden populations. Radio surveys detect neutral hydrogen, tracing gas-rich systems that may be faint in optical light. Each wavelength contributes uniquely to the overall count, producing a more complete census. You breathe slowly as you recognize that counts are also influenced by cosmic variance. The universe is not perfectly uniform. Some regions contain more galaxies than others. Surveys of small areas may overestimate or underestimate density. Combining multiple observations across different regions reduces this bias, improving the reliability of totals. Collaborative efforts enhance precision. Large teams coordinate observations, cross-check detections, and verify classification. Independent measurements using different instruments and techniques ensure that results are reproducible. Estimates evolve as new data is added, but each iteration is grounded in rigorous methodology rather than speculation. You settle into the realization that science adapts naturally to new evidence. The galaxy count changes not because of confusion, but because methods, instruments, and data improve. Each increase in the estimate reflects a deeper, more precise understanding of the universe, rather than a sudden correction or guess. You notice that the process is cumulative. Historical counts provide context for modern estimates. Comparing past and present numbers demonstrates how observational reach directly affects totals. Older surveys missed faint systems. Modern instruments reveal them. The universe appears more populated as measurement becomes more complete. You understand that this iterative refinement exemplifies the scientific method. Hypotheses are tested, instruments are improved, and models are recalibrated based on observation. The increasing galaxy count reflects this disciplined approach, emphasizing careful measurement, repeatability, and honest acknowledgement of uncertainty. Even as numbers change, the underlying physical reality does not. Galaxies exist independently of whether they have been detected. Counts evolve because human observation evolves. Each step is a methodical extension of the previous, building toward a comprehensive understanding of the universe's structure and population. You rest with the awareness that the galaxy count is a product of both observation and method. Improved telescopes, deeper surveys, refined detection algorithms, and careful statistical modeling have increased estimates over decades. This process demonstrates that science is adaptive, transparent, and cumulative, producing knowledge that grows in reliability as instruments and methods improve. Breathing slowly, you notice that the evolving galaxy count highlights the importance of perspective and precision. Each new measurement extends understanding and reveals previously hidden populations. The universe appears richer and more structured as observation deepens, preparing the way for modern consensus estimates that rely on both direct detection and careful extrapolation across the observable cosmos. You begin by considering the most comprehensive surveys available today. Observations from the Hubble Ultra-Deep Field, along with complementary ground-based and space-based imaging, provide detailed information about galaxy populations across a wide range of distances. These data form the foundation for the current best estimates of total galaxies within the observable universe. You notice that astronomers combine deep-field observations with statistical models to account for systems too faint to be detected directly. By examining the distribution of brightness, size, and redshift, scientists estimate how many galaxies lie below observational thresholds. This method ensures that the final estimate includes both observed and unobserved populations, grounded in measurable trends. The resulting analysis suggests that the universe contains far more galaxies than previously imagined. Early estimates based on Hubble's initial deep-field images suggested around 100 to 200 billion galaxies. However, with deeper surveys, improved resolution, and better accounting for faint dwarfs, contemporary calculations indicate there may be over 2 trillion galaxies in the observable universe. This represents a significant increase, reflecting the improved ability to detect and infer hidden populations. You breathe slowly as you recognize that these numbers rely on carefully calibrated assumptions. Astronomers first validate models on nearby galaxies, where distances, luminosities, and population properties are well known. These models are then applied to distant systems, ensuring that extrapolations are based on empirically confirmed relationships rather than speculation. High redshift observations play a central role. Light from the most distant galaxies originates when the universe was less than 1 billion years old. By examining these galaxies, astronomers infer early galaxy formation rates, sizes, and luminosity distributions. These measurements are incorporated into models to estimate the number of galaxies that would evolve into present-day populations, providing a consistent framework for total counts. You notice that different surveys focus on complementary regions and wavelengths. Ultraviolet imaging highlights regions of active star formation, while infrared imaging penetrates dust and captures older stellar populations. Radio surveys detect hydrogen-rich systems that may be invisible in optical light. Combining these datasets allows scientists to construct a more complete census, minimizing observational bias. Even the faintest galaxies contribute to the overall estimate. Dwarf galaxies, many with only a few billion stars, are numerous and pervasive. Statistical methods account for their presence, extrapolating from observed densities in accessible volumes. This ensures that total galaxy counts reflect the full spectrum of systems, from the largest spirals to the smallest irregulars. You settle into the understanding that the universe is structured across multiple scales. Galaxies cluster in groups, filaments, and walls, separated by vast voids. Estimates of total numbers account for this large-scale distribution, applying corrections for cosmic variance and sampling bias. This rigorous approach ensures that calculations are consistent with both local observations and broader cosmological models. Gravitational lensing further supports estimates. By measuring distortions in the shapes of background galaxies caused by intervening mass, astronomers verify that unseen structures align with predicted galaxy distributions. This cross-check provides additional confidence that total counts accurately reflect the universe's true population, rather than observational artifacts. You notice that the 2 trillion estimate remains conservative in some respects. Many faint systems remain below detection thresholds even in the deepest fields. Future instruments, such as the James Webb Space Telescope and upcoming large ground-based observatories, are expected to detect additional galaxies, refining estimates further. The current count is therefore a lower bound, based on reliable, evidence-based methods. You understand that this process exemplifies the careful methodology of modern cosmology. Observation, modeling, extrapolation, and cross-validation work together to produce estimates that are both astonishing and scientifically defensible. The extraordinary number of galaxies emerges not from conjecture but from precise measurement, analysis, and reasoning. You rest with the recognition that each galaxy contributes to the universe's structure, history, and evolution. The count itself provides insight into matter density, star formation rates, and large-scale cosmic architecture. By estimating the total number of galaxies, astronomers gain a clearer understanding of how the universe formed, how it is organized, and how it continues to change over time. You notice that while the number is almost unimaginable, it is measurable and meaningful. Each galaxy is a discrete system, obeying the same physical laws as the Milky Way. Aggregating these systems through observation and modeling produces a reliable census, demonstrating that even vast quantities can be understood systematically through rigorous science. Breathing slowly, you settle with the awareness that modern cosmology combines observation and theory to reach these conclusions. The universe is far more populated than early astronomers could imagine, yet every estimate is based on direct evidence and careful extrapolation. This measured approach allows humanity to grasp not only the scale of the universe but also the processes shaping every galaxy within it. You begin by considering that the number of galaxies is not just a statistic, it reflects the underlying physics of the universe. Each galaxy exists within a framework governed by gravity, dark matter, and the expansion of space. Observing their abundance provides information about the density of matter, both visible and dark, that structures the cosmos on the largest scales. You notice that galaxy counts help refine estimates of the matter density parameter, known as omega_m. This parameter quantifies the ratio of matter density to the critical density required to halt cosmic expansion. The more galaxies observed, the higher the implied matter density, assuming known relationships between dark matter and visible structures. Observations of galaxy populations at various distances provide constraints that are consistent with other measurements, such as cosmic microwave background data. High redshift surveys offer additional insight. By counting galaxies at different epochs, astronomers trace how galaxy formation and star formation evolve over cosmic time. Younger galaxies, visible in deep-field images, reveal the early universe's activity. Comparing early and late populations allows for the calculation of star formation rates, merger histories, and chemical enrichment patterns. These measurements connect individual galaxies to the broader timeline of cosmic evolution. You understand that the spatial distribution of galaxies also carries critical information. Galaxies cluster in filaments, walls, and nodes, separated by voids. Mapping these structures reveals the influence of gravity and dark matter over billions of years. The scale and density of these patterns help constrain cosmological models, including the rate of expansion and the influence of dark energy. Galaxy abundance also relates to the total amount of baryonic matter in the universe. Stars, gas, and dust in galaxies represent a fraction of total matter, while the rest is dark matter. By studying the number and mass of galaxies, astronomers infer how matter is distributed between luminous and invisible components. Observations show that the luminous fraction is small but concentrated in galaxies, while dark matter forms extended halos and filaments that govern structure formation. You notice that the expansion of the universe affects how galaxy numbers are interpreted. As space stretches, light from distant galaxies is redshifted, and apparent brightness diminishes. Astronomers correct for these effects when estimating populations, using models calibrated against nearby galaxies. This careful accounting ensures that galaxy counts are meaningful across cosmic time and distance. Feedback processes also influence galaxy populations. Supernovae and active galactic nuclei regulate star formation, shaping the mass and luminosity distribution of galaxies. Observing galaxy numbers, along with their mass and brightness, provides indirect evidence for these processes. Patterns seen in surveys reflect the combined effects of gravitational assembly and internal feedback over billions of years. You rest with the realization that galaxy abundance is a critical input for understanding dark energy. The accelerating expansion of the universe affects the rate at which structures form. Comparing galaxy populations at different distances allows astronomers to measure how expansion influences structure growth. These observations complement measurements of supernovae and the cosmic microwave background, providing independent confirmation of cosmological parameters. You notice that the cumulative effect of galaxy counts provides a cross-check on theoretical models. Simulations of structure formation predict a specific distribution of galaxies given known physical laws. Observed abundances, including faint and distant systems, confirm that these models accurately represent reality. Agreement between observation and simulation reinforces confidence in current cosmological understanding. You understand that counting galaxies offers more than totals. It informs the history, composition, and dynamics of the universe. The numbers reveal how matter has clustered, how stars and galaxies have evolved, and how cosmic expansion has shaped the large-scale architecture of space. Each galaxy serves as a data point in a vast, interconnected system governed by physical law. You notice that the scale of these observations is both vast and precise. While billions or trillions of galaxies exist, each is measurable in terms of brightness, distance, mass, and composition. Aggregating this information produces a coherent understanding of the universe as a structured, evolving entity, not merely a collection of isolated systems. Breathing slowly, you settle with the awareness that galaxy abundance connects directly to fundamental cosmology. Numbers measured carefully over decades reveal matter density, expansion history, and structural evolution. Each observed galaxy contributes to a larger pattern, providing both quantitative and qualitative understanding. Through these measurements, the universe becomes both vast and comprehensible, and curiosity rests in a calm, measured knowledge of its structure. You begin by allowing your awareness to expand to the full scale of the observable universe. Every galaxy counted, every distant light captured, contributes to a coherent understanding of cosmic structure. The immense number of galaxies, hundreds of billions or even more than 2 trillion, does not overwhelm when considered as measurable systems following consistent physical laws. Each galaxy is a discrete, observable entity. Spiral arms rotate predictably, star clusters evolve in measurable ways, and gas clouds collapse according to gravity and thermodynamics. The universe is not chaotic in the sense of being unknowable. It operates according to principles that can be observed, measured, and understood. The vastness is navigable through careful study rather than imagination. You notice that the distances and times involved are staggering. Light from the most distant galaxies travels for billions of years to reach your instruments. Each observation is a glimpse into the past, providing information about formation, structure, and evolution. Time itself becomes a metric measured by photons, allowing history to be read across space. Observational tools have made this comprehension possible. Space telescopes, deep field surveys, and sensitive detectors have systematically extended human reach. Statistical methods, simulations, and modeling provide context, ensuring that every count of galaxies is not a guess, but an inference drawn from empirical evidence and rigorous methodology. You rest with the knowledge that even hidden components, such as dark matter, are measurable through their gravitational influence. Though invisible, they shape galaxies, guide clustering, and determine large-scale cosmic structures. Observation extends beyond what is luminous, incorporating measurable effects to construct a full picture of the universe's architecture. You notice the quiet patterns revealed by large-scale surveys. Filaments, clusters, and voids form a cosmic web, demonstrating that galaxy distribution is not random but structured. This order emerges from gravity acting over billions of years. Patterns in the cosmos are subtle yet measurable, providing a sense of harmony grounded in scientific observation rather than narrative or metaphor. You breathe slowly as you recognize that human curiosity is both patient and cumulative. Each new telescope, survey, or detection method adds layers of knowledge. Estimates of galaxy numbers evolve as methods improve, reflecting adaptation and refinement rather than uncertainty. Science provides a calm, methodical expansion of understanding, grounded in evidence. Even the unimaginable numbers of galaxies become comprehensible when considered statistically. Groupings, clusters, and filamentary structures allow patterns to emerge. While each galaxy is vast in its own right, the collective population is measurable, with uncertainties quantified and minimized through observation, modeling, and replication. You notice that this perspective transforms perception. The universe is no longer a distant abstraction but a measured, structured domain. Every galaxy represents a point in space with a history, composition, and observable behavior. Through this framework, vast distances, immense numbers, and billions of years of evolution are organized into a comprehensible and reliable scientific picture. As your awareness settles, you feel the calm certainty that comes from measurement and observation. The universe is vast, yet structured. Light, motion, and matter provide the data to understand galaxies individually and collectively. Patience and precision allow humans to grasp cosmic scales, revealing a measurable cosmos in which each system occupies a defined place. You rest with the knowledge that curiosity remains, guided by evidence rather than speculation. Every photon collected, every galaxy counted, reinforces the understanding that the universe can be studied systematically. Vastness and complexity coexist with measurability, and observation provides a path to calm, enduring comprehension. Even in the quiet of night, with billions of galaxies unseen by the naked eye, humanity's observations provide a stable framework. Patterns of formation, evolution, and distribution are accessible to measurement. The cosmos is immense, yet approachable through careful, methodical study, leaving curiosity at peace, steady, and gently sustained by the certainty of what has been observed and measured.